Welcome to a lesson with Dr. Powell. Let's take a look at an example of decomposing a vector into a sum of a vector in a plane and one parallel to a line. That line will be given by the kernel of a linear transformation, this given by this matrix, and the plane is actually given by a right inverse to this surjective linear transformation. Here's the right inverse right here. Meaning that if you compose G on the right side, so we have f of G, that's going to be equal to the identity matrix in the codomain of F. Okay, so first run G and then F, that'll be the identity matrix. So that's what right inverse means. But we're going to look at the opposite order, G of F. And what that actually does is it takes our vector that's in our domain, R3, and it takes it to the codomain and then pumps it back into the domain, but it keeps it in the same fiber. So a fiber is going to be a line parallel to K, and what the right inverse does is it takes something that's in this line, so F will take it to the range, and then when it comes back, it's going to be in the fiber again, but this time it's going to be on the plane, represented by G of R, where R is the range of F. So basically what the function of the right inverse is to take things that are currently on a fiber and send them down the fiber chute down onto the plane. That is the range of that right inverse in the domain. Okay, so that's kind of what it does. So what we do is we start with a point in R3, and what we do is we say, okay, this point is on one of these fibers, and this process tells me what point is on the plane. So what I did, I find that so in doing this, I see that 0, 5, 0 is on the plane. So 0, 5, 0 is on the plane, and 1, 5, -1 is off the plane, but they're on a line that's parallel to the kernel of F. Okay, and that's what we just discovered because they're in the same fiber, and this happens to be on that plane. Okay, so basically what we've done is we've run this into the function F, and then ran that result into G through matrix multiplication to end up getting this right here. This is just simply an illustration that I multiplied these two guys first, and then I multiplied the result to that. Okay, so here's a little picture of what's happening. Okay, so we have a point that's off the plane and the kernel line, and we have a line that's parallel to the kernel, and that's actually given by the subtraction of this point and the point that's on the plane. This is the point on the plane that we just found, and the difference between these two is going to be a vector that is parallel to or that's actually inside of the kernel. So this vector plus that one will be that. How do we find this vector? We just do subtraction. I mean, just take this guy minus that guy, vector subtraction, and we get what's in between. Quite literally, just reminder, vector subtraction. Visually, we have V and W. Think, what's this vector right here? Well, just think about it. W plus this vector is that, so what should this be? Well, the sum will be V, so why don't we just say V minus W, because when we add, the W's cancel and just get V. I mean, algebraically it works, but this gives a pictorial description of this vector subtraction. So from this point to this point, the vector between them is the subtraction. And so, namely, that's how we get a kernel element right there. So that's in the kernel, and then we add to that a vector in the plane, and we get that. We've just decomposed this vector into something coming from the plane plus something that's in the kernel. And so here we have, this is just a little note right here. Notice that when we actually look at F and we want to take it down to Smith normal form. Here's the column operations matrix. This is the basis for the kernel. And notice this is in the kernel. When you take this multiplied by -1, you get the basis vector even. So it's kind of, so that is a little illustration of this is indeed inside the kernel. Thanks for watching.